Light is a wave of electric and magnetic fields. Sound is a wave of air pressure. According to quantum mechanics, all the particles in the universe have the properties of waves, including all the particles that we ourselves are made from. Therefore, to understand light, sound, and the very nature of reality, it is necessary to first understand waves. To understand the properties that all waves have in common, consider a wave traveling along a rope. The wave transmits energy and can encode information. Yet each individual atom stays pretty much in the same spot. For this same reason, if the distance between the wave peaks is much smaller than the size of an object, the object will block the waves. But if the distance between the wave peaks is much larger than the size of an object, the waves will go around the object. In the case of sound waves, the distance between the wave peaks is much larger than most objects we deal with. Sound waves can therefore go around most objects. In the case of light waves, the distance between the wave peaks is much smaller than most objects we deal with. Most objects therefore block the passage of light waves. This is the reason why we can hear things even if there is an obstacle in the way. But we can't see things if there is an obstacle in the way. According to quantum mechanics, all particles are described by waves. The wave describes the probability of where the particle is located. If the particle is given more energy, the wave will look like this. As the particle loses energy to the surroundings, the wave changes. The probability of a particle being at a particular location depends on the wave's amplitude at that location. This means that in this case, the particle has a 0 probability of being in the middle area where the wave's amplitude is 0. The particle somehow transitions from one side of the box to the other, without ever crossing the boundary in between. This means that this is not an accurate representation of how the particle is moving, and there is no accurate representation. Let's try to represent the particle moving in a different direction. As before, how the wave looks depends on the particle's energy. Now let's try to represent the particle moving in both directions. The wave describing the particle now oscillates in both dimensions. How the wave looks depends on how much energy the particle has in each direction. Now suppose that instead of moving in 2 dimensions, the particle is moving in all 3 dimensions. And instead of being bound inside a square box, it is bound by the charge of the nucleus of an atom. As before, there are a number of possible waves that can describe the probability of where the particle is located. These possible waves are what we call the electron orbitals of an atom. Each orbital corresponds to a specific amount of energy for the particle. All the atoms and particles in the universe behave this way, including all the atoms that we ourselves are made of. Waves are at the very heart of the nature of reality.